Hi everyone, welcome back. So far in static timing analysis series, we have covered synchronous timing checks along with other fundamental concepts on static timing analysis. And we have also covered a lot of interview questions based on fundamentals of static timing analysis and synchronous timing checks. So friends, if you have not gone through the first chapter on static timing analysis, I would recommend you to first go through that chapter, and it will be definitely helpful to understand this particular video in a better way. Because in the first chapter we covered what all timing paths are present in a design. For example, synchronous timing paths, asynchronous timing paths, clock gating paths, clock paths, etc. So now let's discuss asynchronous timing checks in this chapter. So as we know, the path here which is present or which is starting from an asynchronous input port to the reset pin, which is asynchronous reset pin of our flip-flop, is nothing but called an asynchronous path. The input port here is asynchronous. That means the toggling of this port is independent of the clock signal. Similarly, the path from the input asynchronous port to the next flip-flop is also an asynchronous timing path. So similar to synchronous timing checks, which are set up and hold, and we discussed previously that the setup check, or actually the setup timing constraint, is nothing but the data at D pin should be stable for some time before the active clock age. And similarly, for hold timing check, the data at the input pin of the flip-flop should be stable for some time after the active clock age. So if this is the active clock age, then the data should be stable before some time of this clock age, and it should be stable for some time after this clock age. So this is nothing but setup time, and this is nothing but hold time. So similarly, we have another timing constraints which are called asynchronous timing checks, because those checks are related to the asynchronous ports of our design, and those checks are nothing but called recovery check or recovery check and removal check. And the recovery time here is nothing but similar to the setup check, where the reset signal here should be stable for some time before the clock age. And like hold check in synchronous timing checks, the asynchronous signal should be stable for some time after the clock age. This is removal time. So hope this is clear. So the relation between synchronous timing check and asynchronous timing check here is very simple. The synchronous timing checks are related to the synchronous pin of our flip-flop, and the asynchronous timing checks are related to the asynchronous pin of the flip-flop. So this is our constraint pin. In synchronous timing check, our constraint pin is nothing but the data pin, which is synchronous, and in asynchronous timing checks, our constraint pin is nothing but the reset pin, which is asynchronous. Now, before going further, let's understand the behavior of our flip-flop when the asynchronous reset signal asserts and de-asserts. So when the asynchronous signal asserts, it causes our output, the flip-flop output to go into a reset value. Normally the reset value is 0. So the assertion of the asynchronous reset is basically not impacted by the state of the clock. And how the very low HDL code of asynchronous reset flip-flop looks like? Code actually looks like this. So if you see here, the always block will proceed as soon as either it gets a positive edge clock or a negative edge reset. So negative edge reset is nothing but our reset is an active low signal. So whenever there is a negative edge reset, that means our reset is basically going from high to low. That means the reset assertion is taking place. So whenever the reset assertion is taking place, irrespective of the clock, our flip-flop will get an output 0. So if you see this behavior through the waveforms, here I have a clock signal and this is our reset signal. So as soon as the reset signal goes low, the output of the flip-flop will also go low. So before this reset, whatever the flip-flop output was, maybe it was 1 or 0. After the reset gets asserted, the output flip-flop output will go to 0 state, irrespective of the clock rising age. So this is the flip-flop behavior during reset assertion. Now let's see the flip-flop behavior during reset de-assertion. So as you can see here, in this code, whenever there is a negative edge of the reset, the flip-flop will get reset. But when the reset de-assertion will happen, the reset de-assertion will happen when the reset signals goes from low to high. So if the reset signal goes from low to high, this always block is not going to trigger based on the reset signal, because the always block is basically sensitive to the negative edge of the reset, not the positive edge of the reset. So during de-assertion, actually, because of only the reset signal, this code is not going to execute. The code will only execute at the next positive edge of the clock. So if you see here, our reset signal got de-asserted. It went from low to high at this point. So this was the rising edge here, and the next rising edge was here, and the reset de-assertion happens somewhat in between. So now when the reset de-assertion happens, our flip-flop output will not change here. The flip-flop output will only change at the next rising edge, because if you see in the code, this code is not sensitive to the positive edge of the reset. It is only sensitive to the positive edge of the clock. So the output of the flip-flop can only change at this stage. It can be either 1 or 0 depending on the data signal, the flip-flop data input signal. Now guys, the important thing here is, if this reset de-assertion happens near the rising edge of the clock, if this happens near the rising edge of the clock, that means it is basically violating our recovery time. So if the reset de-assertion violates our recovery time, in that case, similar to synchronous constraints, our flip-flop can go into metastable state. So this is a problem with the asynchronous reset de-assertion. Here in this chapter, we are only talking about the asynchronous reset. So what is the problem with asynchronous reset de-assertion? The problem is, if the de-assertion happens near the active clock edge, in that particular case, there are chances that our flip-flop can go into metastable state. So friends, an important point to note here is, during reset assertion, there are very less chances or no chances that our flip-flop can go into metastable state. Because as soon as there is a reset assertion, our flip-flop output will go to 0. Even if the reset assertion happens near the active edge of the clock, then also for some time the flip-flop might go into metastable, but usually the reset signals are expected to be applied for quite a long time, and in that particular case, finally our flip-flop will settle to the reset value, and there won't be any issues in the design because of this small metastability caused when reset assertion happened, because finally the flip-flop will be in the reset state. But during reset de-assertion, basically our flip-flop is going from reset state to the normal state. So if there is a metastability in the normal state, that is dangerous, and we have to avoid that metastability. So friends, to avoid this scenario of violating the recovery and removal, in one of our previous chapter, we have covered a circuit solution where we designed a reset synchronizer, and that reset synchronizer basically manipulates our asynchronous reset such that during de-assertion it looks like a synchronous reset. So if the reset is synchronous, that means there are very less chances the reset is basically toggling in the vicinity of the active clock edge, because the reset signal is launched by a flip-flop. So now let's discuss the removal and recovery checks in some more details. So as we discussed, during the reset de-assertion, the control of the output actually transfers from reset line to the clock signal. So basically here the flip-flop is going from its reset state to the normal state. And to avoid the register entry into metastable state, we must ensure that the reset is not de-asserted in certain time frames of the active clock age. So here we need to make sure that the de-assertion should not happen before this point. So the removal time is nothing but the minimum time after the active clock age that the reset must be stable before being de-asserted. So again, I would like to point that asynchronous reset assertion is not an issue as far as flip-flop metastability is concerned, because the flip-flop is finally will be in the reset state after some time. But asynchronous reset de-assertion is an issue as far as flip-flop metastability is concerned, because in this particular scenario, our flip-flop is going from reset state to the normal state. And if in normal state, if our flip-flop is in metastable state, then that might cause the functional issues. So hope the reset removal check is clear. Now let's discuss the reset recovery check. So the reset recovery check basically allows, or it ensures that the de-asserted reset signal allows the clock signal to take control of the output at desired clock age. So that means the de-assertion of the reset should not happen near the clock age, and it should happen before this window, so that the flip-flop can take control of the output at this clock age. Now this is the solutions actually we discussed in our previous chapter. The link of that chapter I have provided in the description section of this link, which was nothing but related to reset synchronizer. So here we implemented the reset synchronizer, which will basically ensure that during asynchronous reset de-assertion, our flip-flop will not go into metastable state. So if we incorporate our reset synchronizer with our design flip-flops, this is how the circuit will look like. This is the additional reset synchronizer, and this is the additional reset synchronizer, and this is the flip-flop in our design. So the output of the second flip-flop, our reset synchronizer, is basically going to all the reset pins of our design flip-flops. So now we have to make sure that our design flip-flops can never go into metastable state. That means we have to make sure the asynchronous timing checks, which are recovery and removal, are not violating for our design flip-flops. So here we have to make sure that our asynchronous timing checks, which are recovery and removals, are meeting the timing requirements. So guys, it is very similar to the synchronous timing checks, which are setup and hold, and there we derived the equations for setup slack and hold slack. Here also for the recovery slack, recovery is nothing but it is similar to setup check. That means our reset signal at this pin should be stable for some time before the active clock age. That means this is exactly similar to the setup. And what is the recovery slack here? The recovery slack will become required time minus arrival time, and this should be as positive as possible. If this is our clock signal, the reset de-assertion should happen before the recovery window. Suppose this is our recovery window, then the reset de-assertion should happen at or before this point, before this recovery window. So what is our required time? Our required time here will become, so the reset is launched by this flip-flop here. So here the reset is basically, the reset for our design flip-flop is launched by this flip-flop. So the required time here will become, this is our clock period, it will become t minus t recovery. And what will be the arrival time? The arrival time will be actually this will be this is nothing but our arrival time, or the arrival path, and this is nothing but our required path. So at this clock age, active clock age will apply to this flip-flop, and the reset signal will be launched by this flip-flop, and it will come to our design flip-flop reset pin. So this will become the arrival time. So if you see here in this particular scenario, our arrival time is nothing but clock to Q delay of this flip-flop. We do not have any combinational logic or something, any kind of skew inserted here also in this particular scenario. So our arrival time will be T clock to Q delay. And what will be our required time? Our required time will be similar to setup time only, where it will be T minus T recovery. In the case of synchronous setup, the required time was t minus t setup. So this equation is very similar to the setup equation, the recovery slack equation, and similarly the removal slack equations will be similar to our synchronous hold equation. So here in the removal conditions, what will happen? This de-assertion actually should not happen after the clock age, or this signal should not toggle for some time after the clock age. So that this time is nothing but t removal, and this de-assertion should happen after this t removal. So this is basically signal propagation and signal arrival. So the arrival time will be t clock to q, similar same, and it should be more than the recovery time of the flip-flop. So the required time here will be t removal, and the arrival time here should be more than the required time to make the removal slack positive. So friends, ideally the concept is very similar to the setup and hold check, but you have to remember that the recovery and removal concepts are there for asynchronous timing paths. Now let's see the another scenario where there is some combinational logic present in the reset path here. So if there is any combinational logic present, then the arrival time actually of this reset signal will be increased by t combinational time. The required time is again going to be the same because there is nothing present in the clock path here. And similarly, the arrival time for the removal check will also increased by t combinational time. If we take the third scenario where there are both combinational delay as well as some skew is also present in the clock path. So in this particular case, our arrival time is going to increase by t combinational delay, as well as our required time will also increase by t skew, because here we are assuming it a positive skew. So the time actually the clock period is actually basically moving right side by t skew. So there is one extra margin of t skew in the required time. So here our required time is going to increase, and because of the combinational delay, our arrival time is also going to increase. For the removal slack as well, our arrival time will be increasing by t combinational delay, and required time will also increase by t skew. So hope this is clear. The concept is similar to setup and hold only, but the paths at which the checks are getting applied are different. For setup and hold, the paths are synchronous paths, and for recovery and removal, the paths are asynchronous timing paths. Now let's concentrate on some important points here. So if you see here, our register 1 D pin is basically tied to VDD. So this will basically become a static signal. So we do not have to worry about any timing checks with respect to this pin. So this is one important concept. But reset de-assertion timing is required for register 1Q to register 2D. So the timing needs to be checked for this particular path. Wherever the data is launched by this flip-flop, it should reach at the input of this flip-flop in 1 clock cycle. So this is something like a synchronous timing check, and here the setup and hold timing checks needs to be met. The third point is recovery removal checks are required for this path. So for this path, or basically our design flip-flop reset pin, for this constraint pin, we need to meet our recovery and removal timing checks, because this is our real design flip-flop and we do not want this flip-flop to go into metastability state. That means we have to constrain this path to meet this is an asynchronous path launched by this, and it is coming to the asynchronous pin of our flip-flop. This is the asynchronous path, and for this path we need to meet our recovery and removal timing checks. The next point is timing at res 1 reset pin is not required, since it is put there to observe metastability and come out of the metastability before the next clock is. What does it mean is, this pin actually, this flip-flop is actually, as we discussed in our previous chapter where we discussed about the reset synchronizer, or this flip-flop can go into metastability state, and that is fine, because our next flip-flop will never go into metastability state, and the output of this flip-flop is only going to our real design flip-flops. So even if this flip-flop goes into the metastability state, it will settle before the next clock age, and it will never force this flip-flop to go into the metastability state. So we do not have to make any timing checks for register 1 as well. Similarly, timing at register 2 reset pin is also not required, since reset get deasserted. The time when the reset is basically deasserted, our input and output of register 2 are going to be 0 state. Because you can understand this in better way in our previous chapter where I discussed about the reset synchronizer, and I will provide the link in the description section. But here I will just touching that whenever there is a reset deassertion happens, input and output of this flip-flop actually during the first clock is going to be same, which will be in a reset state. So there is no toggling happening for this flip-flop, and hence we do not have to make sure any timing checks for this part, for this pin as well. The next point is very important, where we have to make sure that our reset pulse is wide enough that it can be detected by the flip-flops. So if this is our clock signal here, and this was where the reset was basically asserted, and here if it goes to de-assertion state, and if it comes back here itself from de-assertion state, then this de-assertion is basically never going to be detected by either register 1 or register 2. So our reset pulse should be long enough so that it can be detected. So this is very important requirement for the reset signal. Also, we have to make sure that all the flip-flop in design actually gets reset in same clock cycle. That means whenever the reset signal is launched by this flip-flop, it should reach all the flip-flops in our designs in one clock cycle. Otherwise, the purpose of reset synchronization is basically doesn't make any sense. The further point is there can be multiple reset synchronizer per clock domain. So here, if you see here, this is our clock signal. So all these flip-flops are basically getting reset with respect to this clock. If there are another flip-flops and they are basically getting a different clock signals, then we need a different reset synchronizer in that particular clock domain to reset those flip-flop. So how many clock domains in our design are present? We need those many reset synchronizers to be present in our design ideally. And as I said, the reset synchronizer here is basically manipulating the original asynchronous reset to have a synchronous de-assertion behavior. Ideally, it is an asynchronous. This is an external asynchronous reset, and during assertion, the registers, all the registers in our designs are basically resetting asynchronously. But during the de-assertions, to avoid the metastability problems, we have introduced this reset synchronizer. So this reset synchronizer is actually basically manipulating our asynchronous reset to work as a synchronous reset. So that is what the meaning of the 9th point is. Hope this concept is clear. If you have any doubts, please write down in the comment sections. And if you like this video, please hit the like button and do not forget to subscribe this channel so that you won't miss any such videos in the future. Thank you very much.